Welcome to Electron-Line, and now in this video we have a linear object of finite length. Let's say the length is equal to L, and it has some charge on it, some positive charge, and the linear charge density is equal to the charge placed on the object divided by the total length. So by definition, the charge per unit length is what we call the linear charge density. And at some distance away from the object, distance a away, at this location we want to know what the electric field strength is, and of course what the direction of the electric field is. Of course, since this is positive charge, we can assume that the direction will be to the right. And also we're going to assume that this point right here is exactly halfway between one end and the other end. We can move it to other locations right there. We'll complicate things a little bit, but we're going to do the easier case first, where we can see that it's right in the middle. And you can see how a fairly relatively small adjustment you can figure out from a different location as well. All right. So the next thing we're going to do is pick a small little segment. Let's say this segment right here. There's an infinitesimally small little segment, and that would be at a distance x away from this point right here. So that would be this x, and the distance from there to there, that would be a small little dx. And the amount of charge on that little line segment right there, so the amount of charge on there, called dq, would simply be equal to the linear charge density times the length of that segment, which would be dx. So that would be the small amount of charge on there. And then if we draw a line from there to the point of interest, where I want to know what the electric field is right there, and we say that this distance is equal to r, we can then imagine, since this is positive charge, that you're going to have a small amount of electric field at this location due to the charge present in that small little segment, and we can call that little the electric field due to that little segment right there, we can call that a small amount of dE. Now also remember that we're going to have what we would call a horizontal component and a vertical component of that, so we can call this the dEx, and we call this the dEy component of the small amount of dE, small amount of electric field strength right there. Now, as we will end up adding all these little segments together, all the way from one end of the rod to the other end of the rod, we can then imagine we're going to add all those up, and that will then give us the total electric field at this location. But notice that for every segment over here, we'll have another segment down below over here, which will also cause an electric field to exist at this location. That electric field, that small little dE, will be pointed in that direction. And if I pick the point exactly the same distance away from this point over here as I did over there, then of course they will be equal in magnitude. And the angles here will be the same. And you can see that that one will also have a vertical component and a horizontal component like this. Not very vertical, but good enough for now. And you can then see that these two will be equal in magnitude and opposite in direction, and they will cancel each other out. So for every little segment above the line right here, I will have another segment below the line that will cancel out right here, at least in the vertical direction, and the only components that will be additive will be the horizontal components. So the only thing I have to do is simply add up all the horizontal components and forget about the vertical ones, because they will cancel out anyway. So how do I find the dEx? Well, first let's find out what the dE is equal to, the dE, and I don't want to work in green, let me work in black here. All right, so we can say that the dE is going to be equal to the K, that's a constant, that comes from Coulomb's law, times the charge that causes the electric field, which in this case is going to be a small amount of dQ, divided by the distance between this point and the little charge squared, that would be r squared. Now notice, of course, that r, of course this is r and this is r as well, r is simply the square root of x squared plus a squared. So this also here is x. So we can say that this can be written as k times dq divided by r squared, which can be written as the square root of x squared plus a squared, quantity squared. And of course that will negate the radical. And dq can be written as lambda, that would be the linear charge density, times dx. So we say this is equal to k times the linear charge density times dx divided by x squared plus a squared. So that is the magnitude of dE caused by a small little line segment here. Now if I want to find the dEx, then I realize, well, this is the angle right here, theta, which is the same as this angle right here. This is theta as well. And of course, if I then write the cosine of theta is equal to the opposite, no, not the opposite, the adjacent side, which is A, divided by the hypotenuse, which is R, is simply the ratio of the adjacent side divided by the hypotenuse. And so this can be written as A divided by the square root of A squared plus X squared, or X squared plus A squared, doesn't matter, either one. All right, so then I know that dEx, the horizontal component of the electric field caused by one little line segment, is equal to dE times the cosine of theta. Notice that dEx is the adjacent side to the hypotenuse right here. So this is equal to k lambda dx divided by x squared plus a squared, and multiply that times the cosine of theta, which is a divided by the square root of x squared plus a squared. So finally we can write this as a k lambda times dx divided by I like to write x squared first. So x squared plus a squared to the 3/2 power. All right, so now we have the value for dEx, which is the horizontal component of the electric field caused by one small little line segment. Now all we have to do is simply sum them all up, and we get the total electric field at that location caused by the entire rod of charge. Now we're going to be a little bit smart about it, because notice that if I just integrate from the middle point to the top and double it, I get the effect of the whole rod, because the electric field in the x direction from the top half should be exactly the same as the electric field caused by the bottom half of the rod. So if I want to then find the total electric field at this location, remember the vertical components cancel out. This is equal to 2 times the integral of dEx going from 0 to the end of the rod, which would be L over 2, right? This is L over 2, and that's L over 2. That's half the length of the rod. Okay? And that would therefore be equal to the integral of this right here, which is a k lambda times dx divided by x squared plus a squared to the 3/2 power, and integrating from 0 to L over 2. And of course, don't forget the 2 there, because I have to double it since I'm only integrating from 0 to L over 2. All right, now remember that a, k, and lambda are constants. They can come out of integral sign, so this is equal to 2ak lambda times the integral of dx over x squared plus a squared to the 3/2 power from 0 to L over 2. And now you have to remember this integral right there. That's a very common integral. And the answer to that integral is 2ak lambda times, that would be x divided by a squared times x squared plus a squared to the 1/2 power, evaluated from 0 to L over 2. So that's simply the integral of this is equal to that. Okay, so the a squared is a constant that can come out. And then this a divided by a squared will be 1 over a. So this will be 2k lambda divided by a times, when we plug in the upper limit, we get L over 2 divided by L over 2 squared plus a squared, the whole thing raised to the 1/2 power. And then minus 0, because when we plug in the lower limit, we can put 0 in there, of course, we get 0 for the whole fraction. Okay, now we're almost done. So in the numerator we have 2 and L over 2, so the 2's cancel out. And so we can now write this as k lambda L divided by a times 1 over, and we can write this as L over 2 quantity squared plus a squared to the 1/2 power. So that would be the magnitude of the electric field at that location due to a rod full of charge of length L, linear charge density lambda. K is of course a constant from Coulomb's law, and a is simply the distance from the rod to the point of interest. If you now want to write it in a vector format, then all we have to do is put a little vector symbol on here and the directional unit vector, x like that, and now we have it in a vector format. And that's electric field due to a limited size rod of length L at a distance A away from the rod when that point is exactly at the halfway point between the two. Now, what if it's not at the halfway point? Well, if it's, for example, offset over here, then of course you have to integrate it from this location to the top of the rod, however long that is, that should be given, and from that location to the bottom of the rod. So you're going to, the only difference then would be that you have two different limits. The positive limit will be some fraction of L, and the bottom limit will be minus some fraction of L. And the fractions will not be the same, and so there'll be a little bit more algebra involved to get the final answer for that case. But that's how you do that.